This video is just a little walkthrough of this two-leg robot, linear actuator robot, I guess, in comparison to this earlier robot I was working on where the motors are at the joints. This robot has different joints, has more like human joints, which are connected by a rack and pinion gear. This provides a lot more stability. You can see here that it's balanced on one leg and it's holding that position. So I don't want to make too much motion because it can change a little bit, especially on a laminate floor. But you can see the only things connecting it are a power cable and a network cable to this brain back here, which is an Intel NUC, basically. Just a power cable from this power supply right here, 36 volts, and a network cable from the NUC. That's the only thing. The NUC has its own power supply, and it's just a network cable connecting to this robot chassis. So what can I say about this design? Just simply that it's all 3D printed plastic parts. And one of the coolest things about this is, if I get my narrows, this design is that the joints are very much like human joints to a certain extent. The hip uses a ball socket joint, which it gives it motion in two dimensions there. You have also this one-dimensional joint at the knee, which is just simply a hinge joint. It's just connected with a metric 5 screw and an embedded nut in there, which holds it in there. The feet have a couple two-dimensional joints. This is a two-dimensional, or what's also called a universal joint sometimes, I guess, but it's basically a two-dimensional joint, so it can turn forward and backwards, like the foot motor is going to be doing this linear actuator here, but also left and right, which this ankle linear actuator has. Notice also that this linear actuator, or this joint on the ankle, for the ankle joint, is also two-dimensional. It can turn up and down with the foot. There's a screw there going inside it, but also it can turn along what I'm calling the z-axis, which is your roll. It can roll, it can pitch, basically, and that's also the case for this foot motor thing. So here you can see each joint has an accelerometer mounted on them. Accelerometer gyroscope. Basically, it's a single device. Here is the foot one is just mounted there flatly with Y forward, X to the right. The leg one is buried back here. This one has Y minus up, X to our right, I think, or X to the robot's right. Sorry, this is all X to the plus to the robot right. And then, okay, if I get my narrows. So the foot has one, the lower leg has an accelerometer, and the upper leg also has an accelerometer, also mounted similarly to the lower leg with a minus Y up, X to our left, X plus to our left. So to connect these three, we have an ETH Excels. This also can handle 14 touch sensors also, which you can put on the foot. This foot I've covered with some silicone. Otherwise it will slip around and slide around. There needs to maybe be a better solution. I think with touch, I've had touch sensors on there, and they also need to have silicone on there to really provide a lot of friction. Friction is really essential, or else they will slide around. So you have these sensors. They all connect with RJ12 cables into this ETH accelerometer. Let me see if I can start getting those. Yeah, it is actually currently. Here we can see the left leg is pulling in some samples, and that's every 10 microseconds, giving us those angles and the orientation and the actual samples to the orientation of each body segment. For example, the lower legs at -2 pitch, I guess, pretty much straight up. the upper leg has a 10 degrees pitch, which is showing its positive pitch. Positive pitch is back. If you pull back the plane, that's positive pitch. Okay, so moving up the body, we have this leg. In the back is actually the knee, a very long knee rack. Again, it doesn't really look great. It looks kind of mechish or whatever, but it has the holding strength. As you can see, it's standing here on one leg. Also this rack provides a little extra support for standing on one leg, which really is important if you're going to take a step, and you're going to be standing. All your weight, just as humans do, is over one leg. It's really important to be able to have a stable stand on one leg, so that helps out. They're just coincidentally. I mean, isn't that wonderful how that happened to work out that way? So moving up the body, we have two. Notice that there is no ability currently in this design to turn the robot leg in the yaw to give it some direction. So that's one thing I want to add there. And I have a feeling that I could just simply add the similar design to this robot hip, one that just has a direct connection to one of these small motor shafts, because it doesn't take a lot of torque or strength to turn these legs when they're up in the air. So you don't really need a rack. The rack would provide a lot of stability, and it's important to have a lot of stability that the shaft really cannot provide. So potentially I may even want to do a small little rack design in there for turning that, for that hip motor. Okay, so moving up the robot, we have the leg motors, which probably could be a little bit smaller rack. I think this is a 30 centimeter. It could be maybe a 25 centimeter. Also, you can see there's two types of racks. A thin profile, which is 10 centimeters, 20 by 10 millimeter rack versus a 20 by 20 millimeter rack. You can see how the thinner 10 millimeter rack tends to bend a little bit. I'm not sure if that really is going to be an issue or a problem, whereas the 20 by 20 certainly will not bend. But the 10 by 10 looks a lot more sleek, looks a little less, can be a little closer to the body. This side motor is unaesthetic. I think doesn't really have it doesn't look great. I was able to pull it a little bit closer and make it look a little better than it did, if you can believe that. So you have your leg motors, which lift the leg up and down. This one you can see. One of the greatest things about this rack and pinion design is you can see when the two motors are unequal, when you're trying to balance it and level it, because clearly one rack is not equal with the other one, right? Here you can see that this rack is not equal with that one. That one's more pulled up. So that's kind of cool. This design here, this middle piece, which has the two ball joints, I'm calling the hip or waist, but pretty much the hip. And you can see there are no hip motors, two hip motors to turn the legs, as I said. There is a torso motor, though. This design, I added a torso motor because I think a torso motor is kind of important to shift that big upper body weight very precisely. It's important because that is a huge weight, especially with the arms and head. This has no even arms or head. To be able to have a motor to quickly move that massive upper weight forward or backwards, even probably left or right to a certain extent, might help. But that pretty much is not. I mean, otherwise you would have to use the two leg motors, and that's a little trickier because they're also doing other things like stepping and who knows what. So the torso motor is kind of nice. So the ETH motors is on the back. The thing that controls up to 12 motors, and there are 11 motors on this particular design, is back here on the back of this. So this torso is really just basically a piece of plastic where all the PCBs are screwed on, with little spacers. So I'm using the two hip motors for the torso, or one of those hip motors for the torso motor, and I've just remapped it in software. I'm not sure what is the future of that. Maybe the torso motor will have to be the upper body. I'll have to add another ETH motors on there for upper body motors. But anyway, this works currently for now. Then also, so we have two ETH accels, one on each leg, three accelerometers on each leg, one for each segment. I have also so an upper body, a torso ETH accels, which has the accelerometer for the waist, for the torso, and for a head. There's no head on here, but that would be what one would be for. So they're connected again with RJ12s. All these three ETH, all four ETH modules are connected to this ETH switch. This is a 16 port ETH switch, rapidly sending those samples. Also, there are a couple voltage regulators. If you can see here, let's see. Yeah, here there's one. There's another one, I think, back there. One is, I had to use two, in fact, because these PCBs draw a lot of current. And I just found that using two voltage regulators down to 3 volts just keeps them a little bit cooler. So what else? There's a torso accelerometer there. It's in fact, the waist accelerometer, which you can see there, or the hip, I guess, accelerometer, which is the one that is mounted with the opposite X, the third option for mounting an ETH accel up. Is it gonna fall? No, it held. Okay. It's very stable, just incredibly stable. So here I have a little thick wire hook, which I hook on this carabiner, I guess, connected to this gantry. I want to make a future enhancement will be just a really low cost, I think I'm using a metal conduit like EMC basically, or EMT, electric metal tube, just to bend it and make a nice little smaller gantry, to hold this. But it can pretty much stand on its own. It doesn't really need to be, connected to tethered, but I have a feeling that not having it tethered can sort of wear on the motors a little bit, but in this particular design with the rack, mostly it's the rack, I think, that's taking a lot of the weight there. So, probably the motor isn't really stressed too much for that. But I mean, can you imagine a human standing like that for hours? I mean, I know I couldn't really very easily. I certainly would not want to. So I don't think there's anything else to say. Just basically a brief walkthrough of this robot design. It's been a lot of fun to build it. It was just an idea. I had read that Boston Dynamics was using hydraulic linear actuators, and I thought, well, let's give it a try, because with this robot, it was like the stone of Sisyphus. It's like just really tough. I couldn't really stand it on one leg, and I think it's all about leverage. The motor joints, and those are even bigger motors and heavier motors than these. Just the shaft of a motor does not provide a lot of leverage, and so this rack and pinion design really turned out to be, surprisingly, to a certain extent, so far at least, has turned out to be a pretty productive, rewarding design.